Chapter 17. Alcohols and phenols. Alcohols contain a hydroxy group attached to a saturated carbon with sp3 hybridization. The simplest alcohol is methanol. Methanol is a common solvent, a fuel additive, and produced in large quantity. Ethanol, which is also called ethyl alcohol, is a solvent, fuel, and beverage. Phenols contain a hydroxy group connected to a carbon in benzene ring, and a double bond connected to hydroxy group is called enol. An alcohol with hydroxy attached to a primary carbon is called primary alcohol. This carbon is primary because it attached to one carbon. And this is a secondary alcohol because this carbon connects to two carbons. And this is a tertiary alcohol. Here shows common names of some alcohols. Remember, benzene as a substituent is called phenol, and benzene with a methyl as a substituent is called benzyl, and so this is called benzyl alcohol. This carbon connect to a double bond is called allylic carbon, and this is called allyl alcohol. Here is a tertiary carbon with 4 carbon, so this is called tertiary butyl alcohol. Ethyl group with 2 hydroxy is called ethylene glycol. Ethylene glycol is used as an anti-freezer in cars. Propyl with 3 hydroxy is called glycerol. Glycerol has a sweet taste and used as a sweetener in food industry. In systematic naming of alcohols, first you choose the longest carbon chain containing the hydroxy group. For the longest carbon chain, there's a corresponding alkane, and you replace the ending E by OL. So OL means it's alcohol. Now here is how you number the carbon. Number the chain from the end near the hydroxy group. So hydroxy group is in priority compared to alkyl groups. And then number the substituents according to the position on chain, listing the substituents in alphabetical order. Okay, so let's look at the first molecule. So first molecule, the longest chain is 5, so it is a pentane. Okay, pentane. Now it's an alcohol, so replace E by OL. So now this becomes pentanol. All right, but where is the alcohol? It's number 2. You go from left to right. You put hydroxy on number 2. Okay, if you go to the right to left, then that would be number 4. So from left to right give you hydroxy on the lowest number carbon. Okay, so this is number 2 has a hydroxy. Therefore, the name is 2-pentanol. So 2 means its number 2 carbon has a hydroxy. And then you also have substituents, and substituents also in number 2, and therefore it's 2-methyl 2-pentanol. Now let's look at the second molecule. Second molecule, cyclohexane. So this is cyclohexane. Now E should become OL because it's an alcohol. But you have 2 of them, so it's a cyclohexane diol. All right, and where are the diol? Is number 1 and number 4. Okay, so it's number 1, number 4 cyclohexane diol. Okay, now the last molecule. So you go from left to right. The longest chain is 4. Note that here benzene is a substituent called phenol. Okay, whenever benzene is a substituent, the name is phenol. Now, if you go to the left to right, number 2 will be hydroxy. Number 3 will be the phenol group. If you go to from right or left to right, okay, from left to right, then number 2 is the phenol. Number 3 will be hydroxy. All right, because hydroxy is in priority, so you should go from right to left. Give number 2, give hydroxy number 2 carbon, and therefore this is 2-butanol. Okay, because number 2 has a hydroxy, so it's a 2-butanol, and the substituent phenol is 3, so 3-phenol 2-butanol. When benzene has a hydroxy group, it's called a phenol. Okay, so the naming should use phenol instead of benzene. And because you have a methyl group at the metal position, so here is the metal position, so you call metal or M-methylphenol. If you have more substituents, okay, as the second molecule, okay, so it's a phenol. Okay, this is a phenol, and the carbon connect to hydroxy is automatically become number 1 carbon, and so number 1, 2, 3, and 4, and therefore the name should be 2,4-dinitrophenol. Similar to water, alcohols and phenols contain polarized oxygen-hydrogen bond. Oxygen partially negative, hydrogen partially positive. This partially negative oxygen, partially positive hydrogen forms hydrogen bond between adjacent molecules. And because of this hydrogen bond, alcohols and phenols have much higher boiling points than similar alkanes. In an alcohol, the oxygen contains 2 lone pairs of electrons. These lone pair electrons can attack a partially positive charged hydrogen, forms an oxygen-hydrogen bond. In this reaction, this alcohol serves as a weak base. In an alcohol, the oxygen-hydrogen bond is polarized. This bond can break, and the alcohol can deprotonate and serves as an acid. So alcohol and phenols are both acid and base. How do we know an acid is a strong acid or weak acid? We look at the Ka, which is called acid constant. Acid constant is similar to equilibrium constant. It's the product hydronium ion divided by reactants, not include water. So the larger the Ka, the more hydronium ion is produced, the stronger the acid. Now, pKa is defined as negative log Ka. Because you have a negative sign, so a larger Ka means a smaller pKa. And therefore, the smaller the pKa, the stronger the acid. This table shows acidity constant for some alcohols and phenols. In general, phenols have smaller pKa than alcohols, and therefore phenols are stronger acids. Remember, a compound is an acid if it can deprotonate, forms an anion. The more stable this anion is, the easier for the reaction to proceed, and the more protons can generate, the stronger acid. So we look at the stability of the conjugate base of this acid. Phenol, when it deprotonates, all right, it forms phenoxide. And this benzene ring can resonance the negative charge, stabilize the anion. And that's why phenol is a stronger acid than typical alcohols. Among the alcohols with electronegative atom, fluorine, here nitrogen, amino means nitrogen, sulfur, these compounds has smaller pKa, and therefore they are stronger acid than those without any electronegative atoms. On the table in the last slide, we show that electronegative atoms such as nitrogen, fluorine make alcohols stronger acid. On the other hand, alkyl groups make alcohols weaker acid. And you can think about these alkyl groups as electron donating group. So they donate electron to make the oxygen more negative charge, and therefore make it the anions less stable, and therefore alcohols becomes weaker acid. In addition, solvation effect is also important. In alcohol solution, the negative charged oxygen is stabilized by water molecules. Because water has positive charge, hydrogen can stabilize this oxygen. On the other hand, if you have, if a alcohol has many alkyl groups, this make the negative charge of the oxygen sterically less accessible and more hindered and less easily solvated, and make it less stable. And therefore, T-butanol has a pKa 18, is larger than methanol, which has a pKa 15.54. That means tertiary butanol is a weaker acid. Electronegative atoms or electron withdrawing groups take electron away from the negative charged oxygen through carbon-oxygen, carbon-carbon bond, and this is called inductive effect. Okay, so compared to the right side molecule, in the left side molecule, all hydrogens are replaced by fluorine. And this makes this anion so stable that the corresponding alcohol has a pKa only 5.4. So the corresponding alcohol is OH, 3-trifluoromethyl. Okay, so this alcohol has a pKa 5.4, which means that this alcohol is even stronger acid than phenols. When an alcohol such as methanol is mixed with a strong base, the alcohol will lose a proton, forms alkoxide. If alcohol is methanol, the product is methoxide. If alcohol is ethanol, the product is ethoxide. Because alcohols are weak acids, stronger base is needed for the reaction to proceed. A base such as ammonia or even sodium hydroxide can only convert a certain percent of alcohol into alkoxide. In order for 100% conversion of alcohol into alkoxide, strong bases are needed, such as amide, sodium amide. Okay, so remember amide, that's a very strong base. Hydride, sodium hydride, so hydrogen with a negative charge, very strong base. Grignard reagent, okay, you may remember Grignard reagent, so CH3 negative charge, magnesium bromide, and that's very strong base. Okay, alkoxide that formed, all right, is also a base, a good base, similar to hydroxide, and they are widely used in organic synthesis. Here shows some examples to make alkoxide. You can use metals, you can use hydride, amide, Grignard reagent. You may remember that phenols have pKa around 10, which is much stronger acid than alcohols, and usually have pKa around 16. And because alcohols are weak acids, sodium hydroxide is not strong enough to convert 100% alcohols into alkoxide. And because phenols are stronger acids, so sodium hydroxide can convert almost all phenols into phenoxide. We already showed that electron withdrawing groups make alcohols stronger acids. Same thing happens to phenols. For example, phenol itself has a pKa 9.89, which make it a stronger acid than ethanol, which has a pKa 16. If you add a nitro group on the parallel position of phenol, the pKa reduced to around 7. Okay, this is because a nitro group on the parallel position of phenoxide can stabilize the anion by resonance structure. You can draw 6 resonance structure. The more resonance structure you can draw, the more the negative charge is delocalized and the anion becomes more stable, and therefore make the phenol more acidic. Practice: is parallel hydroxybenzoaldehyde more acidic or less acidic than phenol? Okay, so here benzene with a hydroxy is actually a phenol. The substituent is an aldehyde. Aldehyde contains a CO double bond, and that makes it an electron withdrawing group. Okay, it can take electron away due to the oxygen. All right, and electron withdrawing group should make phenols more acidic. And it turns out that pKa is 7.9 compared to 9.89 of phenol itself. Now note that if you add a electron donating group, such as a alkyl group, then that will make molecule less acidic than the phenol itself. Homework: please work on problems 17.1 to 17.5.